Yeah, today we're going to do a little bit more, kind of pick up where we left off last time. Actually, this is the same problem that we didn't quite finish last time. Um, but I wanted to try to streamline the whole process, and so that you can kind of see a pattern in terms of how we're coming up with these volumes. So let's look at these two functions. We've got e to the negative x squared, which is this top function up here, right? And then we've got 1 minus cosine x, which is this bottom function here. So kind of lay this down. There we go. And on the AP test, and even because we're going to be using Desmos, it's going to be a lot more convenient if we give each of these functions a name. So that way, instead of having to write out like 1 minus cosine x over and over again, we could just write like g of x. So let's go ahead and make those declarations here. So I'm going to say we're going to let f of x be, I guess we'll call that the top one, e to the negative x squared. And we'll let g of x be the bottom function, 1 minus cosine x. So that way we can make references to those functions without having to write out the whole thing. Now, the first part is asking for the area of the region. And so this is something that we've been doing since the beginning of this unit, right? On day one, we went over how to find the area between two curves. And the basic idea was to integrate between the two x values that partition the region, and subtract the top function minus the bottom function, right? So let me move this over just a little bit. So the area will equal the integral from 0 to some number. We'll have to find out what that point of intersection is. It's not actually exactly 1. We'll come back to that. Of f of x minus g of x dx. All right, so we do need that upper bound, and so we need to figure out where those two functions are intersecting. So I'm going to type those in over here. We're going to say f of x is e to the negative x squared, and g of x is 1 minus cosine x. So we're looking for this intersection point right here. And I don't know if you can see that, back in the back of the room, but it's 0.941. This x value right here. So that's going to be our upper bound, 0.941. And if you want to give that a name too, you're welcome to do that. If you want to call that A, or that way you don't have to write it over and over again, that would be acceptable too. But yeah, so the area is going to be, the region below the top function, but above the bottom function. So to find that area, we're just going to type that into Desmos over here. And I think I might do that. I might just call that A. So let's just say A is that 0.941, and that way I don't have to type that long decimal over and over again. Just naming that constant there. And so I'm going to say the integral from 0 to A, of f of x minus g of x dx is about 0.591. So yeah, I'm actually going to make a little note here that I'm just calling A 0.941, and that way when I set up my integral, I don't have to write that number over and over again. Okay, yeah, and we've done this before. This is no big deal. I think you guys are good with the area between two curves. Any questions about how to find the area between two curves? I feel like you guys got that down. So let's talk volumes here. So these first couple questions are just going to be kind of a review of what we did last time. This is going to be kind of what your quiz is about. And then on the back page, we're going to look at some different kind of volumes that are a little bit different. but you're still going to compute them very similarly. So the first one is asking us to revolve this region, still dealing with that exact same region, about the x-axis. Okay. Now each cross section will be a washer in this case, basically like a circle with a circle missing. Like if I revolve like this region right here around the x-axis, it's going to create like something. Well, that little circle should be more like that, but something like that. Right? So it's going to basically revolve around the x-axis. And so each cross section is going to look like a washer. In other words, a circle with a circle missing. And how do we find the area of a washer like that? Like just in general, if you want to find the area of a circle with a smaller circle cut out of it, yeah, you don't even have to give me the whole formula. Just conceptually, like you're saying, you find the area of the big circle and you take away the area of the little circle. All right, so this area would be the area of the big circle, which I'll call pi r squared with a capital R, minus pi r squared with a little r. So that would be like the volume of one disc, right? One washer that we cut out there. But there's going to be infinitely many of these. And they're going to go from 0 to 0.941. So we want to add up all those volumes. So the integral is going to go from 0 to that a value, okay, that 0.941, of the big pi times the big radius squared minus pi times the little radius squared. Now in this case, the big radius, like let me redraw this region real quick. Oh, let's get off of there. There we go. So if here's the x-axis, the bigger radius is going to be the value of that function. The smaller radius will be the value of the lower function. Right, here's the big R, here's little r. So yes, ma'am. So we're revolving around the x-axis. So imagine like this curve is going revolving like this, right? Whereas this curve's revolving like this. We're both using the x-axis as the axis of revolution. So here's another way to think about it. Whichever curve is further away from the axis of revolution will be the larger radius. Okay, so since the e to the negative x squared is further away from the axis of revolution on that interval, that will be the larger radius. Does that make sense?
Yeah, thank you.
Yeah. Good question. Now, all of these are going to be set up, all these washer problems are going to be like pi r squared minus pi r squared. Both of those two terms have a constant coefficient of pi. So to sort of simplify, let's write it out and then we can simplify it maybe a little bit later. So let's write it out just like we did last time. Pi times the big radius, which in this case is f, and I'm just going to write f squared, minus pi times the smaller radius, which is the lower function, g squared. Now, when you type that into Desmos, you will have to write like f of x and g of x, but just to kind of get the idea down here. Now, what I was saying a second ago, I kind of got ahead of myself, is that notice that how both of these have a pi, right? And this is going to be pretty consistent on all these kind of washer problems. They're all going to have that pi in there. It's a constant coefficient, so you could factor it out like a GCF, just to make the whole expression a little easier to write. And you can actually factor it, since this is just a sum of these like over and over again, you can factor it out as a GCF outside of the sum. So in other words, you could rewrite this as pi times the integral from 0 to a of that top function squared minus the bottom function squared. It's really the same thing, but I just want to show you like maybe a different way that you might see this written out with that pi factored out. But it's still coming from the whole pi r squared minus pi r squared thing. Okay, now this is something we could just go over here and type in. All right, so we've got pi times the integral from 0 to a of f of x squared minus g of x squared dx, and we get 1.746 for our volume. So as you're trying to figure out how to set up these integrals, I definitely want to encourage you to draw a picture of that cross section to help you see like what it is we're adding over and over again. Like what is the expression inside of this summation? Okay, any questions about that? So that's if the axis of revolution is on the x-axis. Oh, yes, ma'am. Yeah.
Wait, so like you aren't doing the like minus like f of x minus AOR because it's 0? So why you're not writing that?
Yeah, the axis of revolution is just 0, right? It's just the x-axis. Yeah. Now, if it is something else, then we have to adjust the radius. So this is another thing we talked about last time. If the axis of revolution is, in the first case here on part C, below the region, so make a little point here that the axis of revolution is below the region, then the radius will be whatever that function is minus the axis of revolution. So the radius is whatever the function is, I'll call it just y, minus the axis of revolution. Okay, I don't want to call it f of x because we're already using f of x like in here. But so f of x or g of x, whatever the function is. All right, now we're still going to have a situation where we have a washer, but as we revolve around y equals -2, which is down here, so like this is getting revolved around here, the lower function is still our inside, the smaller radius, outside function is still the bigger radius. Or it should be in terms of that function. So yeah, we still have a washer here, which is just, the cross section is just a circle inside of a circle. Right, so the area here, still pi r squared minus pi r squared. But to come up with the radius, we're going to have to add that little extra space since that axis of revolution is a little bit below the region. So here's our setup. I'm going to factor out that pi and write this as 0 from 0 to a f minus -2 would be +2 squared minus g plus 2 squared dx. I got that dx a little too close in there. There we go. All right, so we could type that in. Actually, we could just really just modify this. Don't even have to, well, maybe I'll just highlight and copy and paste this. So we have f of x plus 2, g of x plus 2, and we get 9.172. All right, still same idea, right? Big circle minus little circle, and then we add up all those areas together. All infinitely many of them. Any questions about that one? Now, if we revolve, instead of revolving about an axis that's below the region, if we revolve about an axis that's above the region, let's go back up to this diagram. So if the axis of revolution is like somewhere up here, then the smaller radius is going to be based on the top function, and the bigger radius is going to be based on the bottom function. Okay, now the way to come up with that new radius, I just want to show you well, maybe I'll show you down here. To come up with that new radius, so let me just draw this diagram. Just a little sketch here. Okay, so if my axis of revolution is somewhere up here, the radius, the small radius is right here. This is my little r. Here's my big R. But the way that we're going to come up with both of those radii is to come up with the distance between the x-axis and the axis of revolution, which should just be the axis of revolution itself, right? From here to here, that's just 3, right? And if the distance between the x-axis and the top function is f, then the little radius should be 3 minus f. It's the difference between the height of the function and the height of the axis of revolution. Similarly, if we want the big radius, we can do 3 minus this piece right here, which is the value of that lower function. So when you try to come up with the radius when the axis of revolution is above the region, it's going to be that axis of revolution minus the function, or the value of the function. This is when the axis of revolution is above the region. Now we're still going to have washers here. There's still going to be circles within circles. So the way that we come up with the volume of each washer is going to be the same. The surface area here, the base area, is still going to be pi r squared minus pi r squared. But be careful on the revolution where the axis of revolution is above, because the big one, the big radius, is actually now defined by the lower function, not the upper one. Kind of flips on you on that one. So we're going to have, for our volume, pi times the integral from 0 to a. Now to get the radius, we're going to subtract the function's value from the axis of revolution, which is 3. So 3 minus g squared minus 3 minus f squared. So I'm going to have to kind of modify what I've got down here. I want 3 minus g as this first radius. And I want 3 minus f as the second one. So I got 9.392. As that volume. So that's kind of a summary of what we did last time, right? Found area of a region, volume when you revolve around the x-axis, volume when you revolve around an axis that's below the region, and then volume when you revolve around an axis that's above a region. Now, before we move on from that, anyone have any questions about any of these? Or just the concepts in general? Okay. Well, what if we didn't actually revolve around anything, but we knew what the cross-section looked like, but it wasn't circular? Like we weren't like revolving around an axis. Like for example, let's say you have a pool in your backyard, yeah, and let's say it's the same depth everywhere in the pool. Okay, so it's just a constant height no matter where you are. But let's say you're like, you got a little, say you got a little drone, you're taking drone pictures of your pool. So like an overhead view of your pool. Let's say this region is what your pool looks like from above, right? What we could say is that the depth of the pool being constant would be like that third dimension, right? So how do I say this? Like we might want to find the volume of your pool. Yeah. So in other words, instead of like revolving around here, what if each cross section was something that we knew how to compute? Now I think we'll have one pool problem on here. There won't all be pool problems, but that's just one kind of example of like what kind of three-dimensional object we're going to be finding the volume of. Okay. So let's take a look at E. It says the region R is the base of a solid. So same region. It's still that, might as well redraw it here. Something like this. Doesn't have to be perfect. Here's F, here's G. So that is the base of a region. Okay? Meaning like, almost like you've got a prism, but that's the base area. It says each it's not really going to be a prism, but each cross section perpendicular to the x-axis is a square. All right, I'm going to do my best to draw this. It's kind of weird, but basically, if I take a cross section perpendicular to the x-axis, meaning like going into the paper, like into the third dimension, each cross section, it has to be a square, meaning like the two sides have to be equal, or all four sides have to be equal. So like if I say take a cross section right here, we're going to have like a square kind of going into the paper. It's really hard for me to draw that. Let me try. Let me go a different direction. Right? So you have like a square there going into the paper, but not all the squares are going to be the same shape. Or they're all the same shape. They're all going to be the same size. Like if I find this a cross section, say here, that's going to be a much smaller square. And each cross section will be a slightly different size. All right, so there's a few squares in there. The dotted region means it's like into the page. Yeah, really, it's kind of hard to show it. Hopefully you can visualize it though. So like each line segment in between F and G is a side length of the square. So how do we compute that side length though? We know our cross section is a square. Okay, first of all, how do we find area of a square? Well, we could be even, it's the same, base is the same as the height, right? So it's just whatever the side length is squared. But what is the side length going to be? How do I find this side length? What's the distance between the point on F and the point on G? Well, maybe let me give you some numbers and see if you can just kind of use your intuition here. Let's say the value of F at this point is 10. It's obviously not 10 because we're not going that high, but just say it's 10. And say the value of G right here is 1. What's the distance between them? So this is 10 units up, and this is just 1 unit up. How far is it between them? Yeah, 9. Yeah, how'd you get 9? 10 minus 1. Yeah, take the big one minus the small one. Yeah, so that side length is going to be f minus g. It's going to be whatever the top number is minus the bottom number. That gives you the distance in between. Like over here, like let's say this was like at 2 and this was at 3. The distance between them would be 1. All right, so now we're ready to find the volume. Okay, so the volume is still going to go from 0 to A, which is that point of intersection. The area of this cross section, though, is not going to be pi r squared anymore because it's not a circle, it's a square. So it's just going to be the side length squared. In other words, f minus g squared. So remember, whatever goes here, like this expression, and this is going to be different depending on what shape you're dealing with, is the area of the cross section. That's the a of x from the very beginning. And so, of course, we can type this into Desmos. Maybe I can delete some of these other ones. Just give myself a little bit more space here. Integral from 0 to a of f. Will it let me do f minus g? I don't think it will. No, it's got to be f of x, g of x. Okay, so we get 0.461. Any questions about that one? Yeah. So the f minus g is the distance between the functions. That is going to be the side length of this square that's coming out. Okay, so the reason why it's f minus g is like, let me give you the example I was using earlier. Like, let's say the value of f was 10 here, and this is 1. The distance between them would be 9, right? So you have 1, and then plus 9 would be 10. So the way you can come up with that is doing the value of f minus the value of g. In other words, like going back up here, if I want the distance between here and here, what I could do is take the distance between the x-axis and f and subtract the distance between the x-axis and g. All right, so this is f, this is g, this is the difference between them. And that's determining the side length of the square. So the square is like, this is a side, and like say the square is coming out like this. Yeah. Or it could be going backwards. It doesn't really matter which direction it's going. Does that clarify it?
Yeah.
Yeah, we'll just leave that on there. Okay. All right, so the next one, similar problem here. It says the region R is the base of a solid. Okay, so it's a base. For this solid, each cross section is a rectangle. So instead of being a square, it's going to be a rectangle where the height of the rectangle is 4 more than the base of the rectangle. Okay, so same kind of idea as, I don't really have enough room to sketch this out, but still kind of like this, except instead of these being squares, they're going to be rectangles where this side length will be, what did it say, 4 more than the other side length. All right, so we've got this rectangle. With a base and a height. And we know the area of the rectangle is base times height. But let's figure out like what is the base and what is the height. Okay, the base is like this line segment in between f and g. So it's just like the last problem where it's the difference between those two values. Okay, so the base, this little b here, is f minus g, right, this distance. And then sort of like think of like the depth of the pool, right? How far in is it going? is 4 more than that base. All right, so the height in this case would be f minus g plus 4. 4 more than the base. Now, it doesn't really matter like which one gets the plus 4. It's all going to be the same. You can get the same output. So don't be too stressed about that if you were even thinking about that. So yeah, we'll find our integral from 0 to a once again. Except we have base times height. This is really like what the cross section is going to be. Right? So we've got the base, which is f minus g, times the height, which is f minus g plus 4, and then dx. Okay, well, let's type that in. So we have f minus g. Instead of being squared here, we're going to multiply by f minus g plus 4. And we get about 2.824. Any questions about that one? All right. We got just a couple more for you here. Letter G, the region R is the base of a solid. So same kind of setup. But in this section, each cross section is perpendicular to the, or each cross section perpendicular to the x-axis is a semicircle, where the diameter lies on the region R. So this one I think is worth it trying to sketch out here, at least attempting. So we've got this. So if we've got a semicircle, then basically like the diameter is going to be that distance between F and G. Okay, and then that is the diameter of your semicircle. So your semicircle's like kind of going into the page like this, and you got a bunch of these little, it's a little hard to tell, but they're going like either into or out of the page. It doesn't matter which direction. But in other words, it's like, this should be like half of a circle. So the cross section here is a semicircle. What's the radius, though? Now, we know the area is going to be half pi r squared, but what's the radius of that semicircle? Yeah, f minus g is the diameter, right? That's the distance from here to here is f minus g, but the radius is just half of that. So yeah, the radius here is half of f minus g, or f minus g divided by 2. Okay, so we have the integral from 0 to a. We're going to have 1/2 pi r squared. So 1/2 pi, where r is 1/2 times, maybe it'd be easier to write this as like f, you know what, I think it might be easier to write this as f minus g over 2. It's the same thing, but I feel like it's getting kind of messy the other way. Squared. Now you could factor out, the 1/2 pi, that's a constant factor. We could pull that outside. It's not really going to change much of how we write this, but you could see it written like that. All right, so that's something we could just type in. Got the integral from 0 to, what was that, like point, I've forgotten at this point, 941, I think, of 1/2 pi times f minus g over 2 squared dx. So yeah, we get 0.181. Yeah.
I'm confused. If it already has the 1/2 of the pi r squared, why are you having another 1/2 for the radius?
So these are like referencing two different things that are happening. So this initial 1/2 is because we're finding the area of half of a circle, right? So a complete circle's area would be pi r squared, but since it's a semicircle, it's just half of that, right? Now, as far as the radius is concerned, if we look at this diagram over here to the left, the diameter of that semicircle is f minus g, right? F minus g is the distance between the functions. The radius is half of that. So in other words, like the radius is like from here to here, which is half of the distance between f and g. So one's talking about like half of a circle, the area of half of a circle. One's talking about the radius here is half of the diameter. Does that make sense? Yeah, so you just have like, two instances of a half.
Yeah.
All right, just got two more here. So H says the region R models the surface of a small pond. At all points in R, at a distance x from the y-axis, the depth of the water is given by this function. H of x equals 5 plus x. Find the volume of the water in the pond. Now, we're still going to have like a rectangle situation here. Like if you try to envision what's happening, the depth is given by 5 plus x. Now, that's going to be different for every x. But at every x, it's going to be fixed. So, not every rectangle here is going to have the same depth, but this depth here is whatever 5 plus x is. So instead of being like 5 more than the other side length, it's determined by wherever the x value is. So it's still going to be like a rectangle problem. You have your base and your height. Area is base times height, where the base is right here. Okay, that's the f minus g. And the height is 5 minus x. Oh, plus x, not minus x. Plus x. All right, so we've got the integral from 0 to a. Of f minus g, that's the base, times the height, 5 plus x.
F minus g plus 5 plus x.
Because the height's defined in the problem as just being 5 plus x. Yeah. The reason why it referenced the f and the g before is because it was based on that distance. It was 5 more than the other side. Yeah.
Why did we choose to do a rectangle?
Because, like, let's say x was 2. Or I guess x couldn't be 2 in this scenario. Let's say it was like 1. Or 1's not in the interval either. Let's say it's 0.5. Okay? So 0.5 being like right here. So at 0.5, what's the depth of the pond? So the depth of the pond is 5 plus x. So at x equals 0.5, what's the depth going to be? Right. So whether you're like the distance that you're going into the page, like if this is at 0.5, then this, let me not use black there. Let's use maybe green here. This distance, like into the page, would be 5.5, but so would this one. It's the same x value. So they have like, no matter where you are along this cross section, the depth is consistent. It's always 5 plus whatever the x value is. So all along here, like each one of these depths is 5.5. So this would construct a rectangle. Yeah. When like, so this is like your height. This is your base. Right. So this would be 5 plus the x, and this is the difference between the f and the g. Does that?
Yeah.
See? Now, yeah. Mm-hmm.
It's hard to visualize.
Yeah. If the depth is defined in terms of x, it'll always be a rectangle.
Okay.
Now, so yeah, let's try another one. That's basically the same setup here. The only difference here is they don't give you the depth here. They just give you the area of the shape. So you have no idea what the shape is, right? Even if you try to draw it, you basically can't, because we don't know what that shape is. Like we know here's a cross section, right? But like, what's the shape? We don't know. But it doesn't really matter because they give us the area. And all of these integrals are going to be set up the same way, right? It's going to be the integral of the area times dx, the base area. So this one's 2 over x plus 6. We don't really have a diagram here because we don't know what it looks like. But we can still compute the total volume going from 0 to a and multiplying the base area times dx. Dx is the height. It's the height of each disk. Oh, because before they didn't give us the area. They gave us like the dimensions, right? Like before, like on this one, they gave us like the base and the height of the rectangle, but didn't actually tell us the area. This is the area. So this is your base times height. You know what? I didn't type in the last problem, or this one. We'll get a 2 for 1 here. So let's see what this first one will be. All right, we got 3.155. Okay. And then for the last one, we got 2 over x plus 6. Okay, so we have 0.291. Okay, any questions?